Good afternoon, everyone, and a warm welcome to another webinar. In this session, we will walk you through an important aspect of structural design, the design of shear walls in ETABS, and the methods available within the program. Whether you are new to ETABS or have been using it for some time, having a clear understanding of how shear walls are modeled, analyzed, and designed is essential for achieving reliable and meaningful design results. We will look at the process step by step with a focus on the key concepts and practical aspects that can help you better understand and confidently use ETABS for shear wall design. Thank you for joining us today. Let's get started. So this particular webinar session would be an extension of a previous discussion on shear walls, which was webinar number 10. You can refer back to those discussions, and the video is available to you already. So previously we had discussed the general aspects related to the modeling, analysis, and design. Here in this session, we will be discussing the methods available within the shear wall design module in detail. Okay. So I will start with the modeling options, and then the discussions will enter the design, like when and how to use the simplified CNT or uniform or general reinforcing. And along with that, we also give our recommendations. In the modeling, we have been modeling, for those who are new to ETABS, we have modeling directly in your structural model as a 2D shell element, or you can utilize the ready wall stacks for frequently used shapes that you are looking at on the screen. Yeah. So the image shows the wall stacks. You can quickly define them and then dimension them and use them with peer labels, automatic peer labels. Program can do all the things for you. So it'll be very easy to model the walls. And then we focus on the analysis model, which is the meshing part, right? Typically, walls, planar walls are not meshed unless significant out of plane bending is expected in the minor direction. Then we should consider the meshing of the walls. So it is dependent on the situation and the model requirement. The program can handle it in both ways, that is manual meshing or automatic meshing. By default, walls are not meshed. And then for the design purpose, we need the labeling. One is the pier, another one is the spandrel. Pier is for the vertical walls, similar to the columns. That design procedure is very close to that. And the spandrels are for coupling beams that are connecting to shear walls, which are subjected to heavy shear force. So the labeling has to be assigned to the select wall objects. It is arbitrary, so user will have to assign this, considering the meshed walls or unmeshed walls, to group the elements and to integrate the forces and make it available for the design. So the design will give you the output as per the labeling. Then we have the analysis and the design section. Analysis, I just mentioned earlier, the analysis section is what you have modeled using the shell elements for the walls. And then the design section is what you have assigned the peer labeling to it, right? And then we have several procedures. Uniform reinforcing, which is the default action program will take. You don't modify anything. And then you have the detailed general reinforcing, an extension of uniform reinforcing, but the control will be available to you to work on the reinforce or the reinforced rebar configuration within the section. And then simplified C and T method for planar walls. Where the design is simplified as axial forces carried by the wall ends and designing those ends. Right. So how these pair and spandrel definitions are made? Very simple. Typically, you'll be assigning the same peer label as long as the wall section is not varying along the height. Typically, it will not vary unless some cases there might be some changes, which I'll show in the next slide. You can keep the same peer label. This program treats each story level peer label as a separate wall member for the design. So in case of the out of plane bending or the other aspects related to the analysis like P delta analysis, you can consider the out of plane bending, and if that is needed, you will have to break the wall at mid height, and you can also label them so that if significant bending moment is expected at the mid height, then the peer label will give outputs only at the top and bottom of the peer label, whether it is a unmeshed wall or a label assigned to a group of shell elements. Only the top and the bottom will have the output, design output. So accordingly, we'll have to choose the labeling. Same goes for spandrel. Spandrels report design outputs only at the ends, the left end and the right end. So unlike beams, the frame members, in which along the length of the frame member, multiple sections will be designed to capture the force variation and the design results. With spandrels, the expectation is that the high forces are expected only at the ends and the ends are designed. Right. So typical labeling, general labeling that we recommend, like the X crossings represents the openings in a wall. And if there are openings and on the left, you can label them as a single. If you see the P2, it is single for the entire vertical. Or if you wish, you can have different labeling even within that to capture the variation of reinforcement within that. Otherwise, it can be a single pair label for the entire height. And then the portion above the opening that represents a spandrel or the coupling beam between the left and right. You can assign the spandrel, and you can also assign a pair label just in case too. If you consider that that design should also be checked. We'll discuss this further. And then we have non-planar walls, which is the main topic of today's discussion. We'll come to this in detail in an example, but you can see a C-shaped wall. It can be L-shaped or C-shaped. So I'm restricting today's presentation for the C. Same, whatever we are discussing here will be applicable to L wall or any other multi-legged non-planar shear walls. So one option is assigning the same peer label P2, what you're seeing on the left. It is allowed. And then on the right, it's a mirror of this. I will show the same model and we'll have further discussion on that. So each leg been assigned with multiple peer labels. So when you do that, what you see in the program is like this, a proper C shape in the graphical window. And internally, it recognizes these to three pieces of rectangle like this. And then you can see a small cutout here for the overlapping this area. On the outer side, there is no wall, unlike what you see in the graphical window. So for the finite element analysis, it's a 2D shell element that we are using. So there is no thickness component as a 3D element. So it is only the thickness uh, property given to this. So what you see graphically is internally read as like this, the second image, the middle one, and then the actual finite element model is just a 2D area object or the line if you see it from the plan. So the dimensions are measured to the center line. That's what you're seeing here as a representational for this out. Now, if you take a multi-leg, the same example here, the C shape, the same pair label of P to C assigned to this. And the legs, the shorter legs, and the flanges, top and bottom, are 1 meter long and 300 mm thick. The vertical one, the web, is 200 mm thick and 2 meter long. Image is just representational, but just to give you what it is doing generally. So it adds up the length of all the legs and reports in the pier detail as length 4 meters. Right? And the thickness is an equivalent thickness because the thickness is varying. This is just to demonstrate how it works. And individually, it will have the actual modeled thickness and length, right? And you can see the AG is 970,000 mm square. Quickly show you this, right? So this is leg 1, leg 2, and leg 3. And individual areas are calculated, thickness into the length. And the total becomes 1 million mm square. And you can see the thickness is computed in reverse. So from the total length is 4. And then from the AG divided by the L, you'll get the equivalent thickness, equivalent area used, and thickness is obtained. And this thickness is used for slenderness calculations internally. And the area reported AG is 970,000 mm square. But that is by removing the outer part of these overlaps. That's how program reads it. Okay, this is just to demonstrate what's happening in the output and what you have modeled. I hope this has given you the clarity on the reporting. Next, enter into the pier design. Okay. So for sake of completion, I'm just mentioning all the other important things. For the analysis, P delta effects, right? It is recommended to include P delta analysis to capture the global lateral drift effects in the analysis itself. And the local effects are captured through the design by the additional moment procedure. Any slenderness in the minded direction where it is expected will be captured through the additional moment. And then program assumes that a P delta is done and the effective length is conservatively taken as unity. The unsupported length, however, will be worked out from the actual connections available at each story level. Imagine if it is a two-story unsupported wall, then the framing connection will be at the lowest level, not at the intermediate side and the next level or any level above. So program can recognize this through the connections of beam members or the slabs meshed at the wall ends. So program can recognize this, and the unsupported length will be used for the calculation of additional moments. So this is also automated within the program. So primarily, there are two design methods, the types available here. So simplified CNT, the tension compression forces will be designed, and the the axial load carrying boundary elements will be designed. Web is ignored in the design, so we'll be providing minimum reinforcement for the detailing purposes. And the actual section design using the uniform or the general, which uses full PMM interaction surface. It generates the PMM interaction surface and designs for all the combination by plotting this demand forces P, M2, and M3. If this point lies within the PM interaction surface for the range of specified IP minimum or IP max in the design preferences, then the design is safe. In any one combination falling outside, the wall design will declare it is a failure condition, right? So how it does internally, this should be understood because this is being widely used. So better understanding of this procedure will help you in taking your design decisions. Now, this interaction surfaces will be based on the 8 reinforcing ratios generated between the specified IP min and IP max. So this is a table given in the program manual. I'm reproducing it here for discussion. So 0.25% to 2%, right? By default design preferences, the ratio is 0.0025 or 0.25% to 4%, right? So you can keep that initially, but when you're dealing with non-planar or the multi-legged wall piers, then you might want to review these. The general idea is to keep this range shorter, and then you can do the iterations until the required rebar is within the specified range, IP min and IP max. Okay, once the surface is generated, or multiple surface for different reinforcement ratios, interpolation will happen within this range. If it is going beyond it, the program will extrapolate. So that's why we recommend you bracket the required rebar ratio within the specified range. Extrapolation will be may not be accurate. So that's the main reason behind. And now this is a 2D representation of that. You can see the PM interaction surface. This is the capacity curve. And then L is the load combination, which is plotted for PU and M2. The other direction, that is M3. So it's a full 3D surface. So ray tracing will be done from the origin to the surface through the demand. And the ratio between this is the demand capacity ratio, OL divided by OC. As long as this is less than 1 or the specified limit by default, which is 0.95, the design is safe. Else program will report it is overstressed. So this is same for both uniform and general reinforcing. Okay. So the design procedure considers minimum eccentricity, slenderness, and the interaction surface generation, full 360, and boundary element requirement checks for seismic cases. All right. If it is a single leg or a rectangular section, so this is for the general reinforcing. The uniform reinforcing is something you can specify. Your program will assume by default a ratio of about 0.2 or 0.3 percentage, the very minimum one, and then the iterations or interpolation within the design cycle will happen, and it will report you the required area of compression or the vertical reinforcement, right? So this general reinforcing is for specifying the rebar configuration manually and update this capacity and check against the demand. So that is the logic behind the uniform and the general reinforcing. And when it comes to multi-leg cross section, LC or any standard configuration for shear wall like this. So throughout this, I'm going to keep the C section for the demonstration. And this is the C section what been modeled and what program has recognized internally from the section designer, right? So this missing piece, something you should understand. But if you want, we'll do it in detail. I will show you how to do it in the example. This is one just completed. So I have specified cross section, updated that cross section, which program recognized, and then updated the reinforcement as well. And then I will use this section of specified reinforcement to give me the demand capacity ratio through the checking option. So I will choose reinforcement to be checked and see the demand capacity ratios. That is the most recommended one when you're dealing with this multi-legged all piers for the design. Okay. The shear design is also listed. This is the same thing which we discussed earlier, so I'll try to skip this. And then for this spandrel, as I mentioned, it is going to design only at the left and the right, and then the flexure. And it also checks for D-beam criteria. So accordingly, the lever arm will be updated when it is L by D is less than or equal to 2.5. And then it calculates both horizontal and vertical shear reinforcements as well as diagonal reinforcements in case of the aspect ratio or the stress limit for all seismic involved load combinations. It will give you how much area required in one diagonal. That will be the output. Okay. Let us switch to ETABS and see some of the models and the modeling. Okay, let me start with the rectangular one to discuss a few things relevant for the general reinforcing and how we use this. Okay, we have a 7-story building and let's see, 2 planar walls. Here, seismic loads are applied. I'll simply go ahead and perform the analysis. Right. So under this set display options, we have the peer labels and peer local access enabled. You'll see this. So the wall on the left is P2 and wall on the right is P3. Both are identical forces. Just to keep them one of these for uniform and the other one will work for general reinforcing. See the differences. And now we use this feature. And we'll also try to design the boundary elements along with this. Okay, now we have done this enabling. Please note the local axis orientation. So one is along the height of the wall, two is in the 1-2 plane, that is along the length of the wall, and three is perpendicular to the wall. So major moment will be about 3. So you see this, and shear will be in the 2 direction. So this local axis orientation is important when you're entering the general reinforcing for designing your own section and reinforcement. All right. Now we can go ahead and perform the design. So these are labeled as P2 and P3. So I can go to shear wall design. Look at the preferences once. Let us set all items to default. And you can see the default IP min and IP max 0.25 and 4%. This is okay. And utilization factor limit is nothing but the demand capacity ratio limit. The program is a threshold. Before any value before this will be safe. After this will be declared failure. You can set it to 1 also. This will be slightly conservative. But this is the default preferences. All right. Now how we actually use this, you can go ahead and hit the design. The program will perform the design. What I will do is I will select these spheres and then go to the design, shear wall design, and we have the option called assign shear sections. Right? In that you can find simplified uniform and general reinforcing. So you can choose uniform reinforcing for the first iteration, M30, and let's say 12 mm at 200 mm, and the clear cover to the vertical bar is 25, and corner bars also 12, right? And then you can perform that design, and you can also check for this provided what is the DCR. Let's do both. So I'm taking you through all of these so that you'll get a better understanding. Let's hit the design. All right. Now let us see the design output. It's a planar wall, so 250 mm thick, 2000 mm long. A simple output directly giving how much is the required reinforcement ratio and the rebar area directly for the top and bottom, right? Okay. So in this output, you also see the boundary element requirement since seismic loads are involved. So we see how much is the edge length is required. So program plots this stresses, a linear stress diagram, and works out against the limit and how much is needed. So there is an iteration within happening to report this. So program only reports the length in this design output. Now we are going to design this boundary element using the simplified CNT. What you can do, process, get back previous selection, and go back to the design, assign previous section. Let's assume all the walls, selected walls will be assigned with the simplified CNT. So the method has been set, but we should also be using the overrides. Now you can see pier section type is simplified TNC. You can change it here also, but that is the uh, step that we follow, simplified CNT, and the thickness and the length. So, yeah, the thickness and length are reported here, but you can specify the uh, dB1 and dB2. So dB1 is the horizontal length along the length of the wall, and specify this. If it is 0, program will uh, calculate this length as required, satisfying the PT and PC max limits. So internally there is an iteration happening, and it will do that. You can also specify how much you want. Let us go with 600 mm. This is for bottom. Let's say 600 for the left and 600 for the right. Same goes for the top. dB2 is the thickness direction. If you want to enlarge the end thickness, we can also do that, modifying only the along the length dimension. Right. Press OK. Now I perform the design. So here you can see boundary elements are designed, and here in the bottommost it is failing, but that's okay. We can revise this, but the requirement was already close to 600. 625 is needed, but it is okay. We restricted to 600. So you'll have to increase it. So for the top, it is okay, and it is reporting how much rebar is required. Yeah, you'll be providing the maximum, and even in the graphical output, it will report the envelope of these two, compression and the tension. 3354 for this. So this is something you'll be deciding whether it is going to be designed this way, I mean detailed this way, or there is a clause in the code that exempts you from doing this boundary element check if the entire wall section is detailed with confined reinforcement. So something at this stage you will have to take a decision and proceed with the design as required for you. Now let us move this further and how to use this general reinforcing here. Okay, let us go to the define general pier sections. You will add a new pier section. So pier 2. You can quickly generate a section from the existing wall pier. Much convenient for most cases. We will have to do certain modification. I will show that in this, or you can also create a new section directly. So both of it will take you to the section designer by pressing this button. Okay. What you're seeing is the cross section, M30. We'll come back to this. Let us update this with reinforcement. If you right click inside this, it will enable you to specify the bar sizes. For this one, it is a tie bar. Let's use 10 dia. Then we'll give a name, polygon, one. All right. Now it has created the reinforcement as I specified. Then I'll right click on this. And then let's say I'll keep this cover as 25. Then the bar size, it's 16, and the spacing of 150 mm. Okay, and apply to all edges. Update. And the corners also will update same, 16. Apply to all corners. So this update is very similar to the uniform reinforcing we already utilized, but with a different ratio. But this now we have updated this with a specific rebar ratio. Now we'll also introduce reinforcement within this section at the boundary elements. How to do this? First, we will draw a reference line for 600 mm assumed. Select the shape, and I want to replicate this by 600 mm X. Then one more, let's say 600 from the right end. Right. So these portions, I'm going to add rebars. First, click this approximately, then slightly away from this so that you'll pick up this bar. Let's change the size to 16, and we'll correct this 43 mm, and the center is 125 mm. Update this. Okay. Then we'll use a replicate. Again to this end, this 600 minus 43, another 43, 514. Right. And do another replicate. Again, replicate this in the negative direction so that it fills all the intermediate gaps here for this reinforcement so that the boundary elements is more reinforced. That is the idea. Minus 150 and 3 times. Okay. All right. Now we will replicate everything here, the other side. So we'll use edit, replicate, use the mirror of a general line. It is 2 meters. X is 1 meter and 1 meter. Y1 and Y2, 0 and 1. We'll create bars inside this. That's it. This is the section, and this is the reinforcement we want to have for this section. And we'll update this to the list here too. So, okay. Right. Once this is done, now we'll go back to the assign peer and use the general reinforcing and use peer 2 for both top and bottom, and we'll use checked, and then we'll perform the design once again. Now what you're seeing here is in the brackets is the area of steel provided in the section designer. When you right click, now it is reporting the demand capacity ratio instead of the rebar required. So this is 0.96. This is acceptable for this provided reinforcement of 9,653. Right? Previously it was around 10,300 or something. But anyway, when you work with the reinforcement bars and how we are providing reinforcement, basically the boundary element enhancement of the reinforcement at the ends, it significantly increases the cross-sectional moment capacity, and that benefit you will get in the output as well. This is what how we use this general reinforcing for the wall. So this is not only for the planar wall, this is the same concept for the C-shaped wall. We'll come to this shear wall as an example. Hope this is fine to you, but you can also do this design of this once again using the general reinforcing peer 2. This time you can switch to design and perform the design. Now it will give you reinforcement that will be slightly higher because I think the limit is set to utilization factor limit. I'm sorry, that is set to 0.95. It is trying to increase it a little bit. That's okay, right? Both ways, you'll see roughly about 2% wall. Now there will be another question: how will be doing this for all this? So many hundred number of walls will be there, or many wall elements will be there. But typically, you should understand detailing is also a key thing in the shear wall design. How you detail the bar, just getting the reinforcement is not the end. You have to provide the reinforcement in the cross section, like more reinforcement in the boundary elements or confinement reinforcements you are adding to this. So all of this will also add up a little bit. So you will be simplifying this, like checking the DCR will be the best choice, and the initial efforts might seem to be slightly overwhelming, but it is good if you do that so that you can create copy of those peers. Typically, walls will have the same cross section for most cases. Um, then, let's say this is a 7-story building, so I can provide the peer 2 general reinforcing for up to third story. What you can also do is you can check when you do this check. Sorry, check on this, and then in the graphical output, you can select peer DC ratios. Right. Once you have this, so this is up to 0.8, you can retain a particular ratio that you can decide depending on the project, and then 0.7 to 0.5, you can retain another ratio. So 2 is sufficient for this. 2 reinforcement, maybe you can reduce the reinforcement. How you detail exactly, you can also get that control in the section designer. So your design and your output will be getting closer to each other this way, right? And you can provide that uh, in 2 stages where you want to change the reinforcement and continue it. At least few stories you will have the same reinforcement. There will not be any sudden change unless there is a sudden change in stiffness like podium level or something like that. So you can work on that, how you want to deal with this. So typically this will be a multi-story building requirement. You'll be deciding on those. Okay, next let us quickly open another model, which is this T-shaped section. So whatever we have gone through so far, it is the same, but here the labeling is different, and you can see uh, on the left it is a single pair label, P2 for all three, and then P3A, P3, P3B multi-leg. Now let us go ahead and perform the analysis and the design. Right? And if we go to assign peer section, we'll use a uniform. Let's use let 200 initially. Reinforcement to be designed. Let's go for the design and have the numbers first. This will be the first step, and we'll perform the design. All right. Now, if you see this, the reinforcement for the same peer label is around 15,886, or about 16,000 mm square. If you look at the individual pair labeling for the same forces, so here on this flange, you can see 7,000, and the web it is another 7,300, and the lower flange it is 5,600. This variation is lost in this. However, the overall section is used in the calculation, but individually, one of the legs might be subjected to heavy loads due to the framing. So this is desperately, I wanted to show you uh, the difference when you're using the same peer label and the multi-labeling, where you could miss. If you use a uniform reinforcement, what we generally do, and then it is the top flange is having this ratio of share here, but the actual requirement will be much higher than this 2 meter wall to this 1 meter flange. Right? Both are almost almost same. Right? So the same reinforcement you can miss such things. So the recommendation here is you design for both. First, you start with the individual labeling so that you know the numbers what's going on in each wall, and then based on the behavior for the force distribution, you should also check the force distribution in the wall. This is a very simple wall, so you'll find mostly uniform distribution across. But if it is a complex one, then you should review the stresses or the forces in the wall and the distribution. And you can find in some members where the axial forces are high or the moments are high, this particular leg will have a different force magnitude. Right? So then you'll have to go with the individual pair labeling on the safer side. So this is about the differences. Now let us go with the general peer. To add a peer section quickly using existing one. So P2 is the combined one. We'll use this, and you can see here, right? Now you can use the same section. This is what program internally also using. Should be sufficient for most cases, but when there is a need that you have to model this cross section exactly same shape you want there, then you will have to modify this a bit. So for doing that, I'm going to use the draw tools once again. For example, we add point, reference points basically, to pick the corners here. Okay, once it is done, you right click on this and you can specify the exact value there, 0 and 1100, that is 1 meter, and this portion another 100 mm. Same here, 2300 and 1100. And then I will do a draw command once again using a polygon so that I will be comfortable with this cross section. Instead of selecting the edges and corners and modifying the existing one, I can quickly draw this section, right? And do a Control A and remove this new polygon which I drew and delete the rest. Now we have a proper C section now. Now to this, we'll enable the reinforcing and we do the same. Now we can update this further, but for time sake, I'll accept the default one. But what this also provides you is this the interaction surface generation immediately as you define the section, and you can quickly check the capacities as you vary the reinforcement, and you know the demand already, and you can use the help of this output. Particular is informative only. Still use it and update the reinforcement uh, quickly, and then press OK and press OK. Now we can use this to one of these walls or for all walls. Central reinforcing. Right. Then you can check the capacities. This is about 0.6. Maybe you can make an economical one. Right. Right. So one last thing on this spandrel, which I wanted to show you is this, the labeling of spandrels. So I created a model where there are spandrels. You can see the elevation, you can see the 3D view here. So there is an opening in the wall that you can focus on this spandrel, which is a coupling beam. So I'll close one of these windows so that all right. Yeah. Let us start with the elevation B. What we typically do is we draw the opening and mesh it with the wall so that the corners are getting meshed, which is required. And you can assign this S1 as a spandrel, a label for this shell, and the output is going to be at the left end, right end. So now we can see unmeshed shell is being used. And then the same, if the shells are meshed like this, so into three pieces, then we are assigning the same S1 label to these three. This is the general recommendation for coupling beams where the forces at the ends are significant, and that is where the design is critical. Okay, so that is the general use. But in case you are having a large span girder modeled using these shell elements, And we want to capture the variation of the forces. Then we will go like this. So you can see S2A, S2B, S2C, basically three different labels to these meshed walls. So program can capture the variation. Although this is a very short beam, the variation may not be significant here, but the idea is to show you how to label these for different situations. Okay, so the design I'm not going to discuss, but the outputs, what you see will be like this. You can see for this one, these are meshed all elements with the same label and a single unmeshed one. If you go to the forces, you still see the same N forces, and the uh, linear variation between these two is maintained for both meshed ones with the same label and unmeshed one. And if we go for this one, now you can see the variations are captured at left and right ends of each spandrel label. So and the design output will be at each spandrel label, left and right, and then you will also see the variation across. But that situation is rare, but this is how the use case of multiple spandrel labels or different spandrel labels for the same beam and the difference. So when you're using different labels, do not use the diagonal reinforcement output, because that is a default. It is enabled when seismic forces are involved. So that will not be applicable. That output you should not use, because it is anyway, it's a longer one. That will not be required. Only barring that output, you can use the rest of it by understanding what the design procedure is. Okay, I hope so. These modeling and analysis and design outputs and the discussion and our recommendations along with that help you in take right design decisions and get a better design output as well. Let me quickly check for any question and answers session. Okay, there is a question regarding the meshing size. Meshing size, we typically maintain around 1.5 to 2 meter square of area, but reasonably square, 1 to 2, you can say, meter square of meshing size. So there is a requirement on the stiffness modifiers. For this, I think you should write us to us. We will look into the model and then we'll be giving you the property modifiers. But there is a general one which I can share you over the mail. Okay, regarding the section designer, what are the control points? Control points are nothing but the surface curve which is generated. So the refinement of this PM interaction surface is also becomes relevant when the section is more complex, especially for any non-planar wall. You should increase the number of curves and points for the generation of PM interaction. You can simply double this, triple this, and you'll get a refined, because all of this are numerical interpolation. So better the refinement, better the results would be. And if there are sharp or small lips kind of projections, you should think whether you should model those small lips. Let's say there is a 2 meter wall and there is a 100 small lip perpendicular leg. These things you can avoid and keep the rectangular section, because that is going to give you the maximum capacity. So So if there is no recommendation of when you should use the outer leg, how much is the length? There is no general recommendation, but uh, if it is more than double the thickness of the wall itself, then you can consider. It's a general one, but you can decide on those after reviewing the forces, because there might be significant force coming perpendicular to the wall to that lip, and then you should model it either using a line element or a shell element with the peer label separately better. So regarding the connectivity, we had a discussion in the previous webinar. Please see that webinar 10 for more details on that. Yeah, if there are openings in the shear wall, will the program give authentic results? This is something, arbitrary labeling that we are following. So that's what I was mentioning. When you have an opening, mesh this. And I also showed a schematic diagram of opening and the walls and the labeling. So you have to separate this. Any discontinuous wall in the same plane, whether it is a window or a door opening, something it is large or small, try to mesh it and go to a different label as a default option if you have any confusions on that. Okay, unless they are connected together, there is no point in having the same labeling, clear labeling. Yeah, the PMM interaction surface, how it is generated, is based on strain compatibility method. This is explained in column design manual as well as the wall design manual. You can review that. Let us know if you have any specific queries on that through our email, support email, please. Yeah, there is a question regarding the beam framing into the shear wall. Um, our recommendation would be it is not necessary unless because we typically do not mesh the walls, so can leave it at the wall end in case if the walls are meshed manually, then there will be stress concentration for that element. So on that situations, you can take this to one element length inside, but you also break the beam at this wall end so that the design computation for the shear design of this beam will not be affected. So the clear length or the end length uh, between the walls or the coupling beam or the beam frame remains unaffected in your design procedure. Um, uh, Design of curved walls. Curved walls are not is not possible because the design procedure is simply orthogonal, and then we'll have to use this option. But the individual elements of that multilinear curve can be designed by assigning different peer labels. But there is no design procedure readily available within the program for curved walls because it would be weaker one. So you should think about it and use a different design procedure as available in your referring code. Yeah, I think I have discussed most of this in the presentation itself. There might be few depending on the project you're working. Please feel free to write to us, support@csasl.in. Thank you all once again for joining us today. We'll meet you in another session. Bye for now. Take care.